So this is chapter 11B, or part 2, of Fundamentals of the Nervous System and Nervous Tissue. The membrane potential of all cells has to do with the change or the difference in concentrations of ions on one side and the other, inside the cell versus outside the cell. So on one side of the membrane versus the other. Ions, remember, are charged, so this leads to a difference in charge. Neurons have a resting membrane potential, just like all cells do. However, they can very rapidly change that resting membrane potential. That's why we say they're excitable. They very quickly respond to changes in ion concentrations, etc. The role of the membrane ion channels, what this says, remember, ions, the positive and negatively charged elements, ions are usually water soluble, so they're hydrophilic, but the middle of the membrane is hydrophobic, so ions cannot easily pass across the membrane. How do they get across it? Well, they need these proteins that will span the entire width of the membrane that will act as gates or channels to allow them then to pass through. There's two main types of these ion channels. There are some that are known as leakage channels or non-gated channels. These are always open. Now they will be specific, so if it's a sodium leak channel, then the sodium ion is always able to pass through, versus a potassium channel, which the potassium is always able to pass through. Now the other type of ion channel is a gated channel, and these will open and close in response to different changes. Now usually there's a shape change that triggers the opening and closing of the channel, and these also are going to be very specific for which ion can move through it. Now what causes the protein to change a shape to either open or close it? It's either chemically, voltage, or mechanically gated. So if it's a chemical gated or a ligand gated, that's a chemical, and that just means that the chemical has to bind to the gate, and that binding is what is going to trigger the gate to open or close. Voltage, it's going to respond to a change in charge, and mechanically, it's going to be a shape change. So the chemically gated, as I just said, it's a specific chemical, and usually here what we're talking about are your neurotransmitters such as acetylcholine. The voltage gated, it responds to a change in the membrane potential or the charge. And the mechanically, it's going to be a physical change in the shape of the receptor. And this is showing examples of these. The chemical here, where initially it's closed, you bind a specific chemical and it triggers the opening. Versus over here, notice it's negative on the inside and now it's positive. So you've changed the voltage, you've changed the charge, and that is what triggers the opening of the gate. So when gated channels are open, the ions are going to be able to diffuse quickly across that membrane, and it's going to be following, the ion's going to be following its membrane or its concentration gradient. So if it's higher on one side of the membrane than the other, it is going to go always from high concentration excuse me, to low concentration. Excuse me. Electrical gradients just mean it's going to go towards the opposite charge. Electrochemical gradient is a combination of a chemical gradient versus the electrical charges. We can actually measure the amount of the resting membrane potential, so when a cell is just sitting there, and we know that it averages to be about a minus 70 millivolts. It can range anywhere from 40 to 90, but it averages around 70. So what does this mean? It just means that inside the cell is slightly negative as compared to outside the cell, because there is this difference in charge that's not equal on either side. It's a difference in charge. It just means that the membrane is what we call polarized. Why do you have these different charges? Well, it has to do, once again, with the difference in the ions. The concentration in the intracellular fluid versus the extracellular fluid, inside the cell versus outside the cell. And it also has to uh, deal with differences in plasma membrane permeability. Just means certain items are more easily passing across the membrane than others. And so this is just showing here that the voltage meter is actually measuring this charge. As I said, it's about a minus 70 millivolts. So inside's negative, outside is positive. So why is the inside negative when you look at the ion concentration? There's more potassium inside the cell than outside. Potassium has a +1 charge. Sodium has a higher concentration outside the cell. Sodium also has a +1 charge. Now, potassium is going to play a large role because potassium is going to naturally want to kind of leak out of the cell. Calcium is typically higher outside the cell. Calcium has a +2 charge. So this is showing, here's your cell membrane. Here's inside the cell. This is outside the cell. So sodium's higher outside than inside where the potassium is. The sodium-potassium pump is going to try to help to maintain this concentration gradient, this difference in it. It does not want the sodium to become balanced or to reach equilibrium on either side of the membrane, nor does it want the potassium to reach equilibrium. This will cause a huge problem. It's going to result in death if it does, because you have to maintain, as we'll see in a moment, this difference in the concentration of the ions. So when we talk about permeability, as I just said, it's the ability of things to move across the membrane through some of the leakage channels, those gates that are always open. Sodium is always moving or leaking inside. There's also potassium leakage gates, and there's a lot more of the potassium than there are the sodium leakage gates. So what this means is the cell is much more permeable to potassium. You have more potassium leaking out. Because they're both a +1 charge, if you have a, let's say you've got 2 sodiums leaking in, so you've got 2 plus charges leaking in, but at that same amount of time you have 50 potassium's leaking out. So you've got 50 positive charges going out, but only 2 positive charges coming in. Do you start to see now why the inside's going to be more negative than outside the cell? So as I just said, more potassium is moving out than with sodium coming in. That helps to get the cell more negative. Now, if you've got all this sodium leaking out, it wouldn't take that long before it would reach equilibrium. And that's going to be a problem. You don't want that to happen. So we have the sodium-potassium pump. That helps to maintain the resting membrane potential. That helps to maintain that the inside is negative and the outside is positive. It helps to maintain that sodium and potassium will never reach equilibrium. And how does it do this? Because sodium's leaking in. It's like sodium's coming in the front door, but you're going to have it go out the back door. As soon as it comes in, you're going right back out again. So the sodium-potassium pump, per turn, if you will, 3 sodium ions are being pumped out of the cell and 2 potassiums are being pumped back into the cell. So the potassium's leaking out and you're going to pump it back in, but you're only bringing 2. Notice you're taking 3 sodiums out but only 2 potassiums in. Once again, that helps to maintain that resting membrane potential, which in essence means you're helping to maintain the negative charge inside the cell. So all of this, what are we talking about? Over here are your leakage gates. Here's your potassium leaking out, but here's your sodium potassium pump down here. And this is your sodium leaking gate. So potassium is high inside the cell, so by diffusion it's going to naturally be leaking out of the cell, but the sodium potassium pump is going to pump 2 of them right back in again. Likewise, your sodium is leaking in, but your sodium potassium pump is pumping 3 sodiums out. You're trying to keep the sodium higher outside and the potassium higher inside. If you don't do that, if you allow it to reach equilibrium, then in a moment when we talk about generating this nerve impulse, generating an action potential, you've already seen that for muscle contraction. If you cannot generate an action potential, which is all dependent upon a sodium rushing into the cell. Why? Because it's lower inside the cell. But if you reach equilibrium, you open a gate, sodium's not going to rush anywhere. It's not going to do anything. You'll never be able to generate an action potential, which means you would never have nerve impulses, which means you'd also never have muscle contractions, which bottom line means you would die. So you've got to maintain this gradient. So to change the resting membrane potential, you're going to have to change some of the concentration of the ions across that membrane, which also means the permeability to those ions to get them to move across the membrane has to change. This can be due or brought about by 2 different types of signals, either a graded potential or an action potential. Graded potential is going to be over a very short localized area. However, an action potential can extend the entire length of an axon. It's this change in the membrane potential that actually is what the electrical impulse is, that allows neurons to receive information, to interpret that information, to send the information to get the appropriate response that's required in that particular situation. The changing of a membrane potential. We have different terms for it, depending on how that change occurs, and it's all relative to what the resting membrane potential is. Depolarization is where you are changing that resting membrane potential. Remember, it's naturally around minus 70 millivolts. With depolarization, you're going to make it more positive, which means you're going to bring it closer to 0, or maybe even go above 0. So you're making it less negative. You are increasing the chances of having a response. Hyperpolarization is when you're changing that membrane potential and you're going to make it even more negative. So it's already at minus 70, you're going to make it even more negative. You might go to minus 80 or minus 90 millivolts. So you're making it even more negative, and basically you're decreasing the chances of generating an impulse. So it's more of an inhibitory type of effect. When we look at this on a graph, which once again, because we can measure it, we can graph it. So let me see if I can get my pointer going here. Excuse me. So here's your time. Here's your measurement of your millivolts. We're at about minus 70 at rest. So if it becomes a little bit more positive, that's depolarization. 0 is way up here. So you're going more positive. You're increasing the chances of seeing a response. If you're wondering why there's this little white line across here about minus 50, that's what we call threshold. If you reach that point, you're going to generate an action potential and you're going to see a response. So you're getting closer to that. Now, hyperpolarization, where you're becoming even more negative, you're moving further away from that threshold point. You're getting further away from 0. basically the line's moving even more negative. So you're decreasing the chances of having a response. So your graded potentials, as I said, are in a localized area. It's not going to be across the entire neuron. It's just in a very short area. It's usually very short-lived, very quick, boom, over. The stronger the stimulus is, the more the voltage is going to change, and it's going to affect a larger area. It's still not the entire neuron, but a larger area, which would increase your chances of getting a response. How is the graded potential started? Because you have opened a gated ion channel. Typically, it's a chemical one, like when acetylcholine binds to a receptor and it opens a sodium gate, and you have that influx of sodium. That's an influx of positive charges. Well, if the inside is negative and you've got this positive charge coming in, you're, in that case, getting a depolarization. Positive charges making you closer and closer to zero. It's less negative. So you would have that change in a short area, small localized area. That's a graded potential. Now, let's say you would open a gate and chlorine would come in. Well, chlorine has a negative charge, so to make it even more negative, that would be hyperpolarization. So you have the stimulus, and you can see right here where initially you just have this little area where you have a change in the charge. Why? Because you open an ion gate. Now, depolarization, what's going to happen, that gate opens, you've got sodium flushing in. Are you going to have the change just stay right there? Well, no, it's going to move. Here's your initial stimulus. It's going to move in both directions away from it. So it's going to spread a little bit. It's still very localized. Now, with greater potentials, the charge will dissipate quickly and it's going to decay and break down. So that's why they only cover a very short distance. And that's just showing a few millimeters, that's it, and it's done. Now, an action potential, this is the way a neuron is going to send a signal from one neuron to another through an action potential because it can travel a much longer distance. Action potentials we do see in muscle cells as well as along the axon of neurons, and that's usually it. It will go over a longer distance, so the entire length of the axon, and you usually have a much higher significant change in the voltage. It can be as much as 100 millivolt change. It can go from -70 to a +30. The action potential is not going to decay, so that's why it's able to cover a larger distance. In neurons, this is the nerve impulse. Now, why does it go a long distance? Why does it last longer? A greater potential involved opening the chemical gate, ion gates. For an action potential, it's due to the opening of voltage gates. And so to generate an action potential, first you have to have a graded potential. And then that stimulates an action potential. Because an action potential is stimulated by the opening or closing of voltage gates, you have to change the voltage to open those gates. So you have to have a change. Something has to happen to change the charge. So the steps for generating an action potential, 4 main steps. Number 1, you're at the resting state. All sodium and potassium channels, gated channels, are closed. Now your leakage or your non-gated ones, those are open. Remember I said those are open all the time. So you've got sodium that's leaking in, potassium's leaking out. Your sodium potassium pump is also all the time on. So it's helping to restore that concentration gradient there. Now the voltage gates, you're going to have sodium voltage gates. Most of these are going to be closed. If you change the voltage, you change the charge on the inside from a negative to a positive, that is what is going then to open this gate, allowing sodium to flow in. Because if you open it, sodium's higher outside, so it's going to flow in. You also have a second type of a voltage gate called inactivated channels. They automatically will be blocked. They open very quickly and then close quickly, essentially. You also have your voltage gated potassium channels. Excuse me. They are normally closed. When they open, once again, because due to change in charge, the potassium is going to flow out. Because it's higher inside, low outside, it's going to flow out. So, excuse me, basically know that these are pretty much closed. And what happens is we're going to see a change here. So we just saw the gates. There's more of the sodium voltage gates than there are the potassium. So you have a greater potential. It opens typically sodium chemical gates initially. So you have a stimulus. It may be that a chemical binds to one of those gated, chemical gated ion gates, opens it up, allows sodium to flow in. Sodium has that +1 charge, so it's bringing that plus charge in, and in a greater potential, it's changing a localized area from negative to positive. It's that change in that charge, that positive charge, that is going to be the trigger to open the voltage sodium gates. So right here, you're at rest. The sodium gates are closed. Chemical binds to a sodium chemical gate, opens it, allows sodium to flush in, and what happens is you have that sodium rushing in. You've got that positive charge coming in. That is depolarization. You're going more positive. That's going to trigger those voltage gates to open. And as one opens and you've got an influx of sodium, more positive charge, changing charge, it triggers more voltage gates to open. More sodium flushes in, changing positive charge. See how all this positive charge is triggering even additional gates to open, and more sodium's flowing in, and you've got all this plus charge coming in. It is activating these gates. You have this huge influx of sodium. It's causing even more depolarization, even the charge to go even more positive. You reach that threshold point, which is between -55 and -50 millivolts, and it's all or nothing type deal. You reach that point and boom, you've got an action potential. If you don't quite reach that, nothing's going to happen. You're not going to see any response. It's like, oh, you were so close, but not quite there. But if you reach that 50, all of a sudden, you have got all this positive charge. It's going to trigger even more and more and more of these sodium voltage gates to open, and you have this huge influx of sodium rushing in, and you're going to jump all the way up to about a positive 30 millivolts. That is depolarization, which we can measure, and we see this huge spike. This spike is because the sodium's just rushing into the cell. You're making it more positive. So now what's going to happen? Well, the sodium gates are going to become inactivated, and they're going to close. When sodium closes, that's going to trigger potassium voltage gates to open. Now think about this for a sec. Both sodium and potassium have a +1 charge. You just shut the door to sodium. So no more sodium's flushing in. No more positive charge coming in. And remember, your sodium-potassium pump is always working. So all those sodium-potassium pumps, they're pumping 3 sodiums out. So you shut the door to positive charge coming in. Your sodium-potassium pump is pumping 3 sodiums out. Yes, they're bringing 2 potassiums in, but you're bringing 3 plus charge out, only 2 plus charge in. So you're getting rid of some of that plus charge. Now, when you open the potassium gates, here's the other catch. Potassium's higher inside the cell. When you open those gates, yeah, that potassium is going to be flowing out. So you have this efflux of potassium. All that plus charge is leaving the cell. So that means if you have all this plus charge leaving the cell, no more is coming in. Overall, inside the cell, it's going to start becoming more and more negative. That is repolarization. Repolarization is when you're becoming more negative. You are trying to restore back to that resting membrane potential. And once again, we measure this on a graph. It's becoming more negative. Here it comes down you're coming down the backside of that peak, sliding down the hill. Why? Because you close the sodium gates and you open the potassium gates. Plus charge is flowing out of the cell. That is repolarization. Now the fourth step is hyperpolarization. Some of those potassium gates are going to remain open for a bit. Your sodium resets. And essentially what hyperpolarization is, you go more negative than what the resting membrane potential is. It's kind of like you overshoot. You're trying to get to that minus 70. You might have hit minus 80 or minus 90. It's kind of like, oop, I just missed that exit. I got to turn around and go back. And you can see it right here. We'll see it clearer on another slide in just a moment. But you've got to restore back to that resting membrane potential. And so this is just a summary. You have rest, the gates are closed, depolarization, sodium, gates are open, repolarization, coming down here, repolarization, close the sodium, open potassium, kind of overshoot a little bit, and eventually restore back to resting state. So as I said, that repolarization is trying to restore the electrical conditions, but it does not restore the ionic conditions. So it's trying to get the charge more negative, but we need the sodium potassium pump to restore the proper. You don't want equilibrium of the sodium and potassium, but you want to restore the conditions so that sodium is higher outside the cell and potassium is higher inside the cell. And once again, this is the most well studied of any of the ion pump channels or pumps gates. We know exactly how it works. And as I said, you're pumping 3 sodiums out and then 2 potassiums in. 3 sodium out, 2 potassium, and it's just going to keep cycling back and forth like that. And I cannot stress to you enough the importance of this. It is maintaining that concentration gradient of keeping more sodium out and more potassium in. You cannot allow it to reach equilibrium. If it reaches equilibrium on both sides of the cell, when you open up one of those ion gates, you're not going to have an influx or efflux. You're not going to have movement in or out because it's balanced. And if you don't have that, you would never generate a graded potential. You would never get a graded potential stimulating the action potential. If you never get an action potential, that means you never have a nerve impulse, which means you can never stimulate your muscles to contract, which means if your muscles can never contract, you're dead. Bottom line. It is critical that you be able to maintain that concentration gradient. Will all graded potentials, all depolarization events generate an action potential? No, you have to reach that threshold point. Like I said, it's about minus 55 to minus 50. If you don't reach it, nothing happens. If you do reach it, we refer to it as that all or none. If you reach that threshold, boom, you've got an action potential. If not, nothing happens. Propagation just refers to that action potential as it moves or is transmitted. It's just moving down the entire axon all the way towards the end. So once you start it, it's self-propagating. Now it will move only in a forward direction. And as we get into it, you'll see in a moment that it moves faster in a myelinated axon than unmyelinated. So this is just where you, like I say, you can record the voltage. So you have your stimulus here, and you just watch as it proceeds down the length of the axon. So all action potentials are alike. The central nervous system can tell the difference between a weak stimulus and a strong stimulus by the frequency of those impulses. The higher the frequency, the stronger the stimulus. And that's all this is showing here. The refractory period is that time period where you've generated an action potential, and until you restore things back to that resting state, the neuron's not going to respond and cannot trigger a second action potential. Why? Because the voltage sodium gates are open. There's two types of refractory periods. Absolute, that's the time from opening the sodium channels until you reset them. And so you are not going to have another impulse during this time. Relative refractory period, it's after the absolute refractory period. Most of your sodium channels have returned to the resting state. Some of your potassium channels are still going to be open. You're still in the repolarization state. On average, probably most of the time, you're not going to be able to generate another action potential. The threshold actually is higher because you haven't restored everything quite back to resting state. Like I said, some of the potassium channels are still open. If, however, you receive a really strong stimulus, it could generate another action potential. So if you look, excuse me, at this graph, here's your initial stimulus right here. This kind of green shaded area. So during depolarization and partway through repolarization, this area is the absolute refractory period. So you cannot respond to another stimulus at this time. You're not going to generate an action potential. This bluish, darker blue area here is the relative refractory period. So yes, you still have some of the potassium gates open. You're not quite back to the resting state. If you had a really strong stimulus, you could potentially, boom, go up again and have another action potential. This graph is also showing, I think, better for you to see resting potential. As you go up the peak, that's the depolarization. Why? Because sodium's entering the cell. Here's your repolarization. Your sodium gates are closed. Your potassium is now leaving the cell, making it more negative. This, you can see much better here. The hyperpolarization. This white line right here, that's the resting membrane potential. That's the -70. You overshot it. Okay, you went even more negative. But you get it back here. So this is hyperpolarization when you're even more negative than the resting potential. So as I said a bit ago, your action potential is only going to be going down the axon from the cell body towards the end of the axon terminus, away from that cell body. It only goes in one direction. How fast is it going to go? Well, there are a couple factors that play into that. The diameter of the axon. The larger the diameter, the less resistance you have, and so the faster the impulse is going to go. And myelination. If an axon is myelinated, if it has that insulation around it, it's going to go much faster. So your fastest example of a nerve impulse going down the axon is going to be with a very large myelinated axon. That would be the fastest. Excuse me. The slowest would be a very small diameter fiber that is not myelinated. Continuous conduction is slow on the non-myelinated axons, and then the saltatory conduction, that's only with the myelinated. As I said, it's much, much faster. Those myelin sheaths do insulate. They help prevent that charge from dissipating. And this is just showing how the stimulus can move with and without the myelin sheath on it. And here's now with the myelin sheath. MS, multiple sclerosis, is an autoimmune disease. Usually affects young adults. It's usually when the diagnosis is made. What happens with MS is that the myelin sheath in the central nervous system, they basically are attacked by your immune system, and they are destroyed. The myelin sheath becomes destroyed, and it turns into these lesions. Sclerosis is what the lesions are called. If you're destroying that myelin sheath, the rate at which that impulse is going to be conducted down the axon slows down. Eventually, it can cease. And so it's one of these things you can make the diagnosis on certain symptoms and then additional tests. You may have a few symptoms and then they may go away. You may go into remission and then you may not have symptoms ever again, or they may reappear later. There is no cure, but there are drugs that help to kind of modify the immune system because it is an autoimmune disease. Just be aware, usually if you're taking any type of medication for an autoimmune disease, probably your immune system is compromised, which means you're going to be more susceptible to infections of anything that's going around. So just be aware of that. What are some of the symptoms of MS? Visual disturbances, weakness, loss of muscle control, oftentimes speech disturbances. I have a friend of mine in graduate school was diagnosed with MS. She was in her mid-20s, early to mid-20s, when she was diagnosed. The way she knew something was wrong, she started seeing double and went to the doctor. They ran a whole series of tests and they said, "We think you have MS." Now, her vision ended up clearing up on its own. And so they said, "Okay, you are in remission, but you still have MS." And unfortunately, it's one of those diseases where they can't tell you the range of severity of symptoms that you're going to have or when it's going to happen. I mean, she was frankly told, "You're in remission. You may remain in remission the rest of your life." We don't know. This could come back with a vengeance, and you come out of remission, and maybe in 6 months, you may have not only the visual disturbances again, but you may lose muscle control to the point where you will be confined to a wheelchair in 6 months. We don't know. We just can't tell you that. As you study how the human body is supposed to work and then relate that to disorders and diseases that are interfering with that, you start to realize, yes, we know an awful lot about the human body, but there's still an awful lot we don't know, especially with diseases and disorders and trying to predict when symptoms may occur in a patient. Why does it occur earlier in some people than others? We don't know. There's a lot we don't know. She actually remained symptom-free for about 25 years, and about 5 years ago, she started having some muscle weakness, a little bit of visual disturbances again, and she is now on medication that seems to help with the symptoms, and she's learned not to get overly tired. That makes it worse. But I mean, she is a full-time professor at a university and doing research. So in terms of her career, she's able to work. She's doing quite well. She has a beautiful family, 3 adult kids. Her youngest is in college now. She's got 1 kid in medical school. And so, I mean, she's done quite well personally and professionally. She is not allowed it to define who she is or stop her from trying to reach her goals. It's like, okay, I realize I have this, but I have all my dreams and goals, so I'm not going to let it stop me. It might slow me down on some days, and then I'll deal with it. Local anesthesias work by blocking your voltage-gated sodium channels. So if you block those, you're not going to generate an action potential, which means that sensory nerve that's going up to your brain to tell you to register you've got a pain in your knee because they're doing knee surgery, it's blocked. Cold temperatures or continuous pressure can also interrupt blood circulation and gives that appearance like cold fingers. They'll get numb, or it feels like your foot goes to sleep when you have pressure on it.